Hello my friends, welcome to lesson 20 of a friendly introduction to abstract algebra. We are talking about the very important concept of normal subgroups, factor groups, and in this video the canonical projection from a group to the quotient group, G mod n. So as always, G is a group and n is a normal subgroup of G. Then G mod n can be given the structure of a group itself. And now the canonical projection pi does nothing but send G to its left coset Gn. And we are going to show that this here is an epimorphism, so it's surjective, and the kernel of this epimorphism is exactly n, the normal subgroup we divided by. Of course, to understand all this, I assume that you have watched the last few videos, otherwise this here is a bit too much. I'm not going to explain every time what a normal subgroup is, and so on. Okay, so to prove this, first we need to check that pi is actually a homomorphism. And this follows directly from the definition of the composition of the factor group, because pi of G times H is by definition of pi the left coset of G dot H with respect to n, but this here can be written as Gn times Hn by definition of the group operation of the factor group. This, if you read this backwards, this is exactly the definition how I multiply two left cosets to get another left coset. Well, and this here is pi of G times pi of H, proving, because G and H were arbitrary, that pi is indeed a homomorphism. I could have written two different dots because this here is the composition in G, whereas this here is the composition in the factor group, but I think we're in lesson 20 already. You should get, or you should by now be used to this level of abstraction. So, why is pi surjective? Well, simply by definition of the factor group, because as a set, G mod n is simply the set consisting of all the different cosets, the left cosets, Gn, but these here are exactly pi of G, where G runs through the whole group, and this by definition is the image of pi. So we see that the image of pi is indeed this whole group G mod n, which exactly means that pi is surjective, or an epimorphism, since we already know that it is a homomorphism. Now what about the kernel of pi? An element is in the kernel of pi by definition if and only if pi of G is the neutral element or the identity of this group here, but this here is nothing but the left coset of the identity, or just simply n, and this here is Gn. And now we proved some times ago that this here is equivalent to G being an element of n. So without the lemma we proved some time ago, this here would still require a bit of work, but we use what we have proven before, and this concludes the proof that pi, the so-called canonical projection, is indeed an epimorphism with kernel n. Okay, now we take a look at proposition 22, which is a simple but very important property of homomorphisms. As always, G and H are groups. Phi or phi, I can't decide. In this video I call it phi. Phi is an element of the homomorphisms from G to H, so it's a homomorphism from G to H. And then it is always true that the kernel of phi is automatically a normal subgroup of G. So, We abbreviate the kernel of phi with capital K, and we need to show that this here is true for all elements of G, meaning that K is invariant under conjugation. Actually, for our definition of subgroup, we would need equality here, but we proved in lesson 18, I think, a lemma, that this already is enough for the equal sign here. So if I can show this, I already know that this here is not a subset sign, but already an equal sign. So we take K in capital K and G in capital G, and we take a look at phi of this here. And we need to end up with the identity, because then this guy here lies in the kernel of phi. But this follows easily from the properties of homomorphisms. So first of all, because phi is a homomorphism, I can write this here like so. And again, because phi is a homomorphism, I can pull the -1 out. We proved this in a video about where we introduced homomorphisms. So, but K was an element of the kernel of phi, so I already know that this here is the identity of H. And then I can cancel these two guys, because phi of G times its inverse is again the identity. So I end up with the identity of H, and this shows that this here lies in the kernel of phi, which was the subgroup K. So this shows that indeed K is invariant under conjugation with any element of capital G, because G was arbitrary. And by the lemma I just told you about, we know that here we already have equality, meaning that K is indeed a normal subgroup of the group G. So in short, kernels of homomorphisms are always normal subgroups. This is very important. So there's another proposition. We will not go into the details of the proof. It's not hard, but a bit technical, and my blackboard ends here. So I'm just going to tell you this as a fact. So I take G as always as a group. I take a subset, not necessarily a subgroup, that is non-empty. And then if we have the following condition, that this subset conjugated by any element of G ends up in the subgroup generated by M, then we already know that this subgroup generated by N is a normal subgroup of G. So we do not need to test all the elements of this here. It suffices to test this condition on the elements of M itself. And that this can be useful can be seen in this example here. We want to show, remember, Dn is the dihedral group of the regular n-gon. This is a non-commutative group for n greater or equal to 3 of order 2n. And R is the rotation by 360 degrees divided by n. So this is an element of order n of this group. And the cyclic subgroup generated by R is a normal subgroup of Dn. This is an important example. And to prove this is rather tedious, but using this proposition here it gets a bit easier, because we use the fact that Dn is generated by R, this rotation, and the reflection about any of the symmetry lines, doesn't matter which one. We proved this a long time ago. And we showed that this means that every element of this group can be written like so. R to the k for some integer k, or natural number k, times s. And we do not need the powers of s, because s squared is already the identity. So to prove this, or to give you the idea of the proof, we use this proposition here. M, in this case, is the singleton set consisting of only R. So this is short for subgroup generated by this element here. So all we need to do is check that conjugation of R by any element of Dn ends up in the subgroup generated by R. And this is not too hard to show when you know about the commutation relations between R and S. So this can be done pretty easily, and then you simply use this proposition and you are done. Okay, the details would be a fine exercise for you. If you want to, please feel free to write it down. And that's already it for lesson 20. All right, thanks for watching and see you in the next lesson if you wish. Bye-bye.